Woohoo! Welcome back. Tonight we're going to be talking about 3.5, complex zeros, and the fundamental theorem of algebra. And whenever a mathematician calls something fundamental, you know it's a big deal. So here we go. The fundamental theorem of algebra. Dun dun dun. And it's not going to be what you think it is. It is simply that every polynomial, defined as we've been defining it all the way through this chapter, with complex coefficients. So suddenly we've moved into complex coefficients. So they could be real, they could be integers, they could be imaginary. And the answer is it has at least one complex zero. Dun dun dun. Which is really not what most people expect, because all the way through this chapter we've been talking about how x to the nth should have n zeros, and here we're just saying there's one complex zero. And the answer is that it turns out that just this theorem is just really, really hard to get to. So we get there, and then we're like, yes, we've got one. Because as soon as we have one, then we can factor out that one factor that has that zero in it, and then we've got a new polynomial. And the degree of the new polynomial will be n minus 1. And that one also has 1, and so on and so forth. So proving that it has at least one zero is the trick to proving that it has all the zeros. And that, it turns out, is not the fundamental theorem of algebra, which is surprising. It's actually something called the complete factorization theorem that basically says if p of x is a polynomial with degree n, which is greater than or equal to 1, then there are complex numbers all the way from c1 through cn plus another one called a, such that you can factor polynomial as a constant, so you can factor out a constant, and then a bunch of factors, x minus c. And all the different c's, could be the same value or different values. This is the one that says if it's a cubic, if it's degree 3, there should be 3 factors. This is what we're talking about right here. So a review. There are a couple of terms we're going to talk about, both in the book and today. Multiplicity. If x minus c appears in a factorization of p of x k times, we say that c is a zero of multiplicity k. It means it happens more than once. So we've got twinsies. That's all that's talking about. And we're also talking about the fact that complex zeros come in pairs. So if a plus bi is a 0, then a minus bi, and that has to be true. Otherwise, we end up with all sorts of chaotic things happening in the problems we're going to be doing. Okay, you ready? Dun dun dun! And in fact, the problem that we're going to work on is a throwback. P of x equals x to the 4th plus 50x squared plus 625. And if you remember, you're going to say, wait a minute, we started out being able to do this. We don't need Descartes. We don't need upper and lower bounds. We know how to do this because this is a quadratic type. And I agree. So what I wanted to do was to pick this one because it has some interesting behaviors. But we're going to go ahead and take a look at what's happening here as if we didn't know how to factor it. So that's what we're going to do. So I'm going to say, okay, x to the 4 means there are 4 zeros. That's the first thing to note. And there are different ways to approach it. But what I'm going to do is I'm going to start with Descartes. P of x is plus, plus, plus. Do you see that? Plus x to the 4th, plus 50x squared, plus 625. There are no variations. So there are 0 positive real zeros. So we shouldn't look for any positive real zeros. Okay, that's fine. Let's look at p of the opposite of x. Okay, that's the opposite of x to the 4th plus 50 times the opposite of x squared plus 625. And that's, well, to the 4th is going to gobble up that minus, so we're going to get x to the 4th. Again, squared gobbles up the minus, so we get 50x squared plus 625. There are no sign changes, just like the above. So there are no negative real zeros. So what did we just learn? There are no positive real zeros. There are no negative real zeros. Is 0 a 0? No, that's not going to work. All the zeros are imaginary. By that I mean they're all complex, but they have non-trivial imaginary parts. So the first reason I wanted to do this problem was to show you that sometimes when you approach Descartes, it tells you there are no real zeros. You're looking all in imaginary land. So knowing that, you're going to approach it in a different way, because all of our other methods that we studied, for example, the rational roots, the rational zeros theorem that has the p over q, that only works if there are real zeros. There are no real zeros, so we shouldn't do that. Upper and lower bounds, again, that only works with real zeros. Synthetic division, I imagine there is a way to use synthetic division with complex numbers, but I don't know what it is. So all of our other methods kind of go out the window. So what do we do when this happens? Well, the good news is that we can now remember, say, oh, that's right, we have this other technique where we look at x squared as being part of the quadratic. This is a quadratic form. And in doing that, we can say, okay, well then x squared equals the opposite of 50 plus or minus radical 50 squared minus 4 times 1 times 625 all over 2 times 1. Okay, so that's negative 50 plus or minus. Now this, I'm going to need a calculator. So let's bring in my calculator. Thank you, Sharktopus. And let's see, I've got 50 times 50. That's 2,500 minus 4 times 625 times 1, which is 2,500 all over 2. And all of a sudden, I've got something even weirder happening. As I said, this is a really weird problem. I wanted to do this because in this problem, pretty much everything goes wrong that could possibly go wrong. Or everything goes right, depending on your perspective. So we've got this situation where 0 is in the denominator. I've got negative 50 plus or minus radical 0 all over 2. So that's negative 50 over 2. That's negative 25. Now, up here I said there were 4 zeros. And down here, I get one answer. So what the heck is going on? So let's take a closer look. So what the heck is going on is that when you've got imaginary numbers in play, which is what we've got, there's some weird stuff that can happen. I want to point out that this says x squared equals negative 25. And you'll notice that inside the radical is the 0. So it's negative 50 plus 0, negative 50 minus 0. This is actually 2 answers. They're just twinsies. Quadratic formula always gives you 2, but sometimes they're exactly the same. So what this is saying is that this x squared equals negative 25 counts for 2 different answers. Let me hold there. Let's keep going. So if x squared equals negative 25, let me square root both sides. I need a plus or minus over there on the right. And then I get x equals plus or minus radical negative 25, which is equal to plus or minus 5i. Okay, interesting. So in other words, x equals 5i or x equals negative 5i. And again, at this point, you should be saying, wait a minute, this is only 2 answers, and we said 4 zeros. So let's take a look. I can put these together. X minus 5i, x plus 5i. Now, if I multiply those two together, I get x times x plus x times 5i minus x times 5i minus 5i times 5i, right? So that's going to give me x squared. These two cancel out, minus 25i squared. So x squared minus 25 times negative 1. That's x squared plus 25. Interesting. Now, what is the actual polynomial? The actual polynomial looks like this. These two only get us up to x squared plus 25. What's going on? Well, this was a double answer. So I actually have 2 of these. X squared plus 25 times x squared plus 25. X to the x squared times x squared plus x squared times 25 plus 25x squared plus 25 times 25. I almost ran out of room there. Okay, so that's x to the 4th plus 25x squared plus 25x squared plus 25 times 25 is 625. So we've got x to the 4th plus 50x squared plus 625. That's our original polynomial. So the polynomial in question, x to the 4th plus 50x squared plus 625. Oops. My hand wanted to get through the problem faster. 625. It factors as x squared plus 25 times x squared plus 25. And this is what I meant when I said this counts for 2 answers. When you use the quadratic formula and there's a 0 inside the square root, you end up with twinsy answers. You get 2 of these. So we get 2 matching factors. And then each of these factors as x plus 5i, x minus 5i. So it's x plus 5i squared and x minus 5i squared. So each of these zeros has multiplicity 2. Which is just a fancy way of saying each of them appears twice when you factor it. And does that make any difference? It absolutely does. It does change the nature. It changes the graph. It changes the way the polynomial behaves. And so it is worth looking into. I would encourage you to graph this in Desmos to get a better idea of what's going on. You'll see some interesting things happening because all of the zeros are imaginary. So that's going to make for an interesting graph. But take a look at this and then remember, when you're doing the homework, sometimes everything's going to go wrong. And it doesn't mean that it's a disaster. It just means that maybe you need to ask for some help, or maybe you need to work with another student. Whatever it takes, know that we're here to help you out. And hopefully it all goes well. And hopefully, because you guys are so brilliant and you're so amazing, you will sit down to do the homework and it will all make perfect sense. And that would be amazing. But regardless, feel free to ask lots of questions, and then give yourself a nice pat on the back for making it through this video. And woohoo, we are almost done with the chapter. Nice work. Woohoo. Math on.